All right, could everyone's attention? All right, I'd like to introduce our speaker for today. This is Jonathan Kay from the Lunar and Planetary Institute. He is a postdoctoral researcher there, and his research interests are primarily about studying planetary body surfaces and structure change, such as analyzing and modeling icy moons of the outer solar system. And today he's going to be talking about something interesting. And also, again, I want to remind you guys the Lunar and Planetary Institute is our neighbor, just right nearby, right next to where our new science building is going to be. So if you're interested in the talk, definitely ask our speakers some questions afterwards. And there may be a lot more you could learn and possibly collaborate with. And I do believe they do have a summer internship program. So I'll turn it over to Dr. Kay.
Thank you. I've been at the LPI for about 6 months. Thank you. I started in August. I finished my PhD at the University of Illinois at Chicago in May. So I'm pretty new to this postdoc stuff, but if you guys need anyone to talk to about what it's like afterwards, feel free. I can give you my email address at the end. So what I'm going to talk about today is one of the chapters of my dissertation on formation of the bulge of Iapetus through long-wavelength folding of the lithosphere. I'll explain basically what all of those words mean at some point during the talk. But before that, I wanted to give you a little bit of background info on the Saturnian system and how we know what we know about it. So as you might have heard, the Cassini mission just finished orbiting Saturn. It was launched in 1997. It had about a 7-year flyby to orbital period to Saturn, where it used various gravity assists to get there. The mission ended in 2017 with a big fiery crash, not really fiery, but a big crash into Saturn, which was pretty exciting for us. And we got a lot of really cool data out of that. And it was it's what's known as a flagship mission, which is the highest class of mission that NASA launches. And I think the launch cost was about $2.2 billion in 1997. But this mission, they started planning it in the late 80s. Obviously, these are both artist renditions. And it's a joint NASA-ESA mission, and ESA is the European Space Agency. They actually included a probe on it that landed on one of the moons called Titan. So the Saturnian system has over 62 moons that are larger than a kilometer in diameter. So much like lowering the status of Pluto, we only really talk about 3 or 4 of them because we don't want to make people memorize them all. The big one that you'll see is Titan. It's about 2,500 kilometers in radius. That makes it bigger than our moon. It's actually the second biggest moon in the solar system after Ganymede. I'm actually giving a talk to your geology department on Thursday afternoon, talking about some of the work I've started at LPI on Ganymede. That's a moon of Jupiter. But some of the other ones that are of great interest are Iapetus, which is a personal favorite, and one you might have heard of, Enceladus. But a little bit about some of the notable moons of the system are Titan. We always knew that Titan was sort of mysterious. In the late 70s, we sent 2 spacecraft out called Voyager, which have just left the solar system. But Titan we always knew was really interesting because it has this really thick atmosphere. It's about 60% thicker than the Earth's atmosphere. This atmosphere is made of mostly methane and nitrogen. We have a lot of trouble sort of seeing into Titan with visible instruments. So what we have to do is use radar instruments, and Titan has this haze because of the sort of interaction between the long hydrocarbons and the ultraviolet radiation from the sun. And one of the most interesting aspects of Titan is it's actually near the triple point of methane in temperature. So water on the Earth is near the triple point, which basically means that you can go from liquid water to solid water and to gaseous water. All three can exist on the surface. So Titan actually has all three of these. This is an artist rendition of the Huygens probe that sort of descended through. And this picture on the right is an actual picture that they got at the base of the fall. And so one of the things you'll notice is, A, there's not a lot of visibility, but B, you see these sort of rounded boulders of ice. And I don't know how much geological background you guys have, but one of the things a geologist will notice when you see rounded boulders like that is it means that it had to sort of saltate down a riverbed, which is where sort of the angular fragments get broken off. And so that means that these are likely sort of fluvially deposited. And what we see with follow-up image, so this actually occurred before this image did on the right. This is a visual image. And one of the things you'll see right here and right here are what's known as sort of dendritic river valleys, and that's what you get when you have rain on a mountain that starts to erode, and then these sort of feed into it. So much like the Mississippi has lots of branches that feed into it and then all dump into the Gulf, you see similar things on Titan. And so we do see some large mountains on Titan, large relative to a body in another part of the solar system. So once again, we have this image. But most of the data that we were able to get off of Titan are through this radar instrument on Cassini. And so what you get are these really sort of unusual looking images where you see there are some bright spots and some really dark spots. And it turns out that these dark spots are actually giant lakes of methane. And so they absorb all this radiation, the radar information, and so that's there's nothing for the radar to reflect off of. So we think that they're largely methane and ethane. And one of the neat things about Titan, the more we know about it, is it actually looks like you have this, the ground is this methane ice. And so once you get below that at a certain pressure, there's actually likely a liquid methane ocean underneath. So one of the common themes of the icy satellites in the solar system are these oceans that exist below the surface. Another one of these moons that we sort of had some expectations that Titan was going to be interesting because we knew that there was an atmosphere. But another one of these moons that we really didn't expect anything of was this tiny little moon of Enceladus. So it's about 250 kilometers in radius. Just for reference, this is Great Britain. But we saw this picture early in 2004. I was an undergrad in Massachusetts, and what we're looking at is the south pole of Enceladus. And what you see here is it's illuminated from behind. These are actually active jets coming out of the surface of water. And so what we thought was going to be sort of a boring dead piece of ice is actually incredibly geologically active, actively emitting material into space. One of the ways that we age at one of these icy satellites is we look for craters. And so you'll notice that in this sort of northern part or northern hemisphere, there are a ton of craters. But as we look in this southern polar terrain, you don't see nearly any craters. So these are what we call these tiger stripes. This is where the material was jetting out of the surface. One of the ways that you can generate heat on these bodies is through orbital resonances. So that's where the I don't need to explain resonance to you guys. Basically, these two satellites sort of drive each other into having more elliptical orbits. The more elliptical an orbit, the more energy you can generate, and the more heat you can have. This is another one of these bodies that we think has a subsurface ocean. And if you were to look at a sort of higher resolution image of the South Pole, you would see that there are actually older tiger stripes that occur in orientations that are different from these, that are no longer active. So that's one of the ways we think that it has this subsurface ocean. And so that basically happens that you have this solid core underneath, and then a liquid ocean, and then this ice shell. So the core and this ice shell can rotate at different rates. And if you have any questions, I'm happy to answer them as we go. I know every school does that a little differently. Yeah, so we see both a really young surface and a really old surface. We don't know what causes this dichotomy. Some people think it's an impact, although other people think that planetary geologists say it's an impact when they don't know what it is. It's sort of an ongoing joke in our community. But this is just a contrast of where the plumes are and what the tiger stripes look like. It's a really neat region where there's a lot of really interesting geology and physics going on. Just another image of it. And then these images on the right, these sulcus, are close-ups of the tiger stripes. And we're not exactly sure what's going on in between the regions. Some people think that they're normal faults. I personally think that they're regions of folding, but I'm kind of that's sort of my MO, is blaming everything on folding. Some of other interesting moons of Saturn are Mimas. It's sort of a Death Star-looking moon. That's just a giant ancient impactor, probably early in the solar system. You can see how it's super saturated with craters, and that just means that every time a new crater forms, it erases an old one, telling us it's super old. Then we have this Hyperion. It's sort of more irregular. It might have been captured by Saturn. It looks more like pumice. I don't know if you guys are familiar with that, suggesting sort of a lower porosity material. And then we have Dione, which has these wisps or ice cliffs. We're not exactly sure why those formed or where they formed, why they did. They're not that symmetrical. And then late in Cassini's orbit around Saturn, we found this really weird moon, Pan. And Pan is it's within the ring, so it's probably an object that sort of got gravitationally perturbed and started accumulating material. But it's kind of like two half circles with a playing card in between. So and it also has these weird fractures on it. So that's another one of these weird moons. So that's just 6 of 62. I'm going to talk about Iapetus today. Iapetus has sort of 3 neat things going for it. It doesn't have an atmosphere. It doesn't have any active tectonics, so it's not as well loved among the Saturnian satellites. But it has this alternating light and dark terrain on each hemisphere. We think that has to do with some processes related to I can't believe I forgot the word. So it's a lot bigger than Enceladus. It's about 730 kilometers. It has this really bizarre equatorial ridge. I don't know. From my angle, it's hard to see. It's maybe easier in this angle. This ridge is 20 kilometers tall in places, which is taller than Mount Everest. It's up to 100 kilometers wide. It's not continuous over the surface. It also has this equatorial bulge, which is about 5% flattening, and where the A minus the C is about 35 kilometers. And when I say that, I mean the equatorial radius is 35 kilometers larger than the polar radius, which is a lot. It's about 0.1% on the Earth. So that's what I'm going to be talking about today, but I want to just give a little more background on Iapetus's ridge. So what we think happened is that there was another body that was within the hill sphere of Iapetus, which is basically its own gravitational field. So it's possible that this moon had its own moon. But the moon got so close that it started getting torn apart by tidal effects. And if you tear apart this moon tidally, and it happens slowly, those things will sort of run out of orbital energy, and they'll slowly start to accrete around the equator. And as they run out of energy, they'll slowly bombard the surface with small particles. And if you have enough of them, you can build up one of these ridges. That's sort of the leading idea. One person described it as the least terrible idea I've heard that makes sense to describe this feature. Here's just an oblique angle view of it. So it's got, it's fairly rare in the solar system. We don't see anything else like that, but it's a really cool feature, and a lot of people are interested in it. Just another picture of Iapetus. Sometimes when you're a modeler and all you look at are outputs, it's nice to just look at the pictures every once in a while. And so this is actually the global geologic map of Iapetus. I wanted to put it up because just to show you sort of how little data we actually have on this. Cassini orbited Saturn for a long time, like 13 years, but based on the way sort of the orbital mechanics worked out, we got very little coverage of Iapetus, and so we have very few high-resolution images, and of those, we don't have even global coverage. And you can see this whole region is totally washed out. But to get into what I'm talking about today, I'm talking about this equatorial bulge. Once again, it has this 5% flattening and this A minus C of about 35 kilometers. Okay, so most of my work involves trying to estimate what are the consequences of a certain heat flux on a surface. All of the activity that we see is driven by, on any planetary body, is going to be driven by this internal heat transfer. Be it from sort of the remnant material that drives it, or some sort of orbital resonance. So we have a lot of heat budget on the Earth's interior from radioactive elements, and measurement of this heat flow is really easy on the Earth. You can measure sort of the present day heat flow, but if it's not on the Earth, it's quite expensive to do, and you can only measure the current one, right? We have Curiosity on Mars, which can sort of measure that, but I don't think there's some thermal imaging cameras, and you can estimate this by modeling, which is sort of what I try to do. There are lots of different ways to deform a lithosphere, and lithosphere I just sort of define as the part that you would stand on up to a certain depth that behaves mechanically similar. And so one thing that I like to look at is folding, and that's basically accommodation of strain in contraction. So you get some sort of rectangular surface and you turn that into some sort of periodic topography. This occurs when you have a strong layer over a weaker layer. If it's a purely elastic behavior, so strain that's recoverable till you reach this cohesion point, you get buckling, but there's also a more fluid elastic-viscous-plastic, I'll explain what those mean in a minute, where you can get this sort of folding. So if we can constrain the thickness of this lithosphere, which you can estimate from surface features, it's possible to constrain the thermal history of a body. These material properties occur along a continuum. We call that the constitutive relationship. And you can do that using sort of a semi-analytic model, calculations, or you can look at this process over a continuum using finite element analysis, which sort of solves the matrix equation simultaneously, which allows you to add a lot more detail to the calculations. Just to give you some examples of what these folds look like on the Earth, we see all of these layers were almost certainly straight when they formed. They were deposited horizontally, and then there was some sort of compressional stress, and these were warm and weak, and it allowed them to shorten through some sort of folding process. On a more large scale, we call the way these features deform sort of the yield strength envelope, where basically you have stress versus depth, and depending where you are on this envelope is how things will form. So typically, if you are within this region, you'll get a more brittle form. This is where you would see folding, or if you were to sort of bend a ruler and snap it, that would occur here. And then the deeper you get, the more creep or viscosity-driven parameters will take over. And then we call this transition the brittle ductile transition. For elastic parameters, they're all driven by some simple equations. I wanted to include some equations here so you physicists knew that us geologists knew how to do some math. This is a relationship that basically describes the elastic strength of ice at depth with both zero cohesion and finite cohesion. Basically, does the material have any strength to begin with? And then at depth, once you reach this brittle ductile transition, there are several different creep regimes which take over, which respond differently to some are rate limiting, like easy slip or grain boundary sliding. And then there's differential creep. If you have questions about this, I can answer them here or another time, but this is sort of the relationship that drives the deformation. And then this total will describe the strain rate. So I don't know how familiar you guys are with finite element analysis, but basically using it's sort of like CAD with physics. You can break up any domain into elements. The way I like to describe it is basically I could draw this table in finite element space and then estimate by also including the weight of this, how much this table sort of deflects due to the weight of this projector. Except what I like to do is simulate lithospheres over hundreds of millions of years. And so what this does is it basically solves a series of boundary value problems, and you can break the domain into a series of elements, so that's how they communicate with one another, and this allows for the application of real-world physics. So what I did for this work was simulate the unstable deformation of this lithosphere. Remember, that's that mechanical layer. This is applicable for both long and short wavelength situations. So there is some long wavelength deformation on the Earth, sort of within the oceans and within the basin and range region. This can bypass some of the shortcomings of these semi-analytic models because it allows you to add more detail and have more resolution, as well as other parameters that are difficult to get in purely analytical sense. And to do this, I used the MARC finite element analysis program. You might know ANSYS or Iapetus or something else. These are kinds of programs that are typically used in like aerospace engineering sorts of programs. Okay, so that's the background. So this oblate shape, typically, or originally it was thought that this occurred because of a spinning of a thick lithosphere. So have you ever seen like a tennis ball rotate rapidly and you get those that like deformation where it starts to pooch out on the side? So it was originally thought that basically if you spun Iapetus with a period of about 16 hours, you could it would match the current shape. That's in contrast to the current period of about 80 days. So that means that basically as it was spinning at 16 hours, you shoot it with some sort of freeze ray, and that locks in the shape. That's not really fair. You actually need this thick lithosphere with to support it, right? Because that provides the strength to support this bulge. Because as soon as that tennis ball stops spinning, it goes back to its shape. So we try to estimate the heat budget of these bodies by two ways. There's long-lived radioactive isotopes and there's short-lived radioactive isotopes. These long-wavelength ones create a lithosphere that's too thin to support it because they put too much heat in the system, versus short-lived radioactive isotopes, which create a lithosphere thick enough during despinning because there's not a ton of heat. But this model, because they're short-lived, and in geology, 4 million years is short. This means that Iapetus must have completely formed within 4 million years of these what we call calcium aluminum inclusions. These are these radioactive isotopes that provide the heat. And all of these are what was there when Iapetus accreted around Saturn. So this is a plausible model. The physics works, but it's a really narrow timing constraint for it. An alternative hypothesis is that what if there was a tectonic origin? Rather than something that was despinning, you have a tectonic origin. So it's possible that as Iapetus accreted, and there was this low heat flow, you got all this basically ice together, but the ice was really porous. And by porous, I mean it had a lot of holes in it. So the density was maybe not quite what it would be if it was perfect, pristine ice that you might find in Antarctica. So these guys, Sandwell and Schubert, they suggested that if you have these long-lived radioactive isotopes, it might cook out all of this porosity really slowly, and that loss of porosity would basically import a really large stress onto the surface, which would cause buckling. What they found, though, was that the stresses required to do that were too large, and they couldn't get it to work. But what I thought was, okay, well, we know, though, that these elastic parameters aren't enough to drive the deformation. We don't see that we don't see ice as being purely elastic material. We see it as a more complicated elastic-viscous-plastic material. So I thought, rather than buckling, which is that elastic form of folding, what if we have just folding of this lithosphere to form the bulge? And so we kept a lot of the same parameters. So just some background about my meshes. We wanted to make sure they were deep enough not to be influenced by this flow field. So the width of the mesh was about 1/4 the circumference. So I basically broke Iapetus up into 4 hemispheres and took one and then unwrapped it. I went to a depth of about 200 kilometers. Remember, Iapetus is only 700 kilometers in radius. I looked at a range of heat flows, pretty low, 0.1 to 5 milliwatts. This picture is to remind myself to tell you that it was important to basically not assume that the equator of Iapetus gets the same amount of sunlight at the pole, which means that the equator is going to be much warmer. That's a crucial detail for this model. And then I applied a range of surface temperatures from about 50 to 100 Kelvin. And I used this cosine variation in surface. So if you imagine a square of sunlight at the equator, and then you slowly start moving that square so it stays tangent to the surface, you get about a cosine variation in this in the amount of sunlight or solar flux that you get. And then all of the temperatures are going to be dependent on the thermal models that I picked. So this cosine variation becomes important because if you just sort of squeeze a surface, you will get uniform thickening, and so nothing will happen in the model. So this surface temperature breaks this lateral homogeneity. And basically, the hypothesis that I was working on is that these variations in surface temperature and heat will drive sort of variations from the heat flow to cause preferential lifting of the surface relative to another part. So I assumed water ice properties, and then I applied 10% shortening. So this shortening is coming from this porosity loss, where all of these circles means that it can only move in the x direction, and these can only move in the y direction, and then these red arrows are where I applied the shortening. For most of my models, I did this over about 100 million years, but I also tested to see, 50 or 200 million years. And all of these B's are some of the resultant simulations. And then I used this more sophisticated rheology. Just to illustrate how important both temperature and conductivity are, this is a heat flow of about 0.75 milliwatts per square meter at depth, just to look at how this conductivity profile. So you might be familiar how with most metals or rocks, the conductivity is just a constant value. But for ice, it's actually a function of the temperature that influences how conductive the ice is going to be. So I mostly tested around 3 different parameters because we don't really know exactly how porous the ice is, or basically more fractured ice might have a lower porosity, and so which could decrease the conductivity. And then just to show you how much of a range, I have 0.1 milliwatt per square meter to 2 milliwatt. This is temperature as a function of depth. You can see that at 200 kilometers for my 0.1, I'm at like 110, and for my 2 milliwatt, I'm at 300. So these can have large impacts on the temperature at depth. So I assume ice 1 mechanical properties. That basically means what is the Young's modulus and what's the Poisson's ratio. I applied this 10% shortening. I looked at a range of heat flows, 0.1 to 5, and then I looked at 50 to 100 in these 30 Kelvin increments, and then I also looked at a couple of different conductivities. So my goal is to produce at least 35 kilometers of uplift at the equator relative to the pole. Okay, so some of my most effective models were about half of the normal conductivity value, so that's about 325 over T. That makes the ice at depth a little bit warmer. Here is what you're looking at, 3 outputs of this equatorial minus polar radius, and then time. So you can see how the bulge grows through time. And what you'll see is that 2 of my models here can produce deformations of a little bit over 40 kilometers, and one of them, this 50 to 80, produces a little over 5. So suggesting that this lower heat flow is pretty sensitive, so there's fairly narrow range. I can do this again for 0.75 milliwatts. Once again, you're looking at the equatorial minus polar radius, so we see a little bit warmer now, but all 3 of these, the total deformation is coming down a little, but all of them now are within this narrower range, which is producing more than that 35 kilometers. And then we can also look at what does the conductivity do to it. This is heat flow of 0.75, so the conductivity values seem to be playing a large role in the final deformation. We can also look at what these individual heat flows do. So 60 to 90 Kelvin is what's plotted, this 325.5. Now there are 4 different heat flows here, and you'll notice now it's 2 milliwatts, so we're starting to get too warm for any of that ice to support this bulge, right? We need to be in some narrow window where the ice is warm enough to move relative to the pole. The ice at the equator needs to be warm enough to move relative to the pole, but not too warm that it can't support anything. So in all of these models, or most of them, we're able to produce more than the observed amount of deformation, which is good. That's always good when you're trying to write your PhD. We needed some way to break that lateral homogeneity, so I was able to do that through this cosine surface profile. We found that the deformation was concentrated at these low latitudes, which preferentially lifted them relative to the high latitudes, which sort of makes sense because in those models that were in the sweet spot, the ice at the equator was warmer. And when the ice is warmer, it's a little more mobile versus that ice at the pole, which is a little stiffer. So that ice at the equator started being able to thicken while the ice at the pole didn't really want to move. Some caveats to some of this work. I implicitly assumed that Iapetus was fully differentiated. That means that basically it's separated versus density. So like the Earth is fully differentiated. If it was undifferentiated, the ice would probably be a little bit stiffer, but it would have a lower bulk density and a lower volume fraction of rock. So I don't think this would expect the conclusions to change too much. I also didn't do this in spherical geometry, which didn't include sort of the membrane effects of it. This would make the lithosphere more resistant to change, but that's also kind of mitigated by the fact that I was able to, in almost all the success models, I could produce more deformation than is presently observed. So that leaves some wiggle room for not having the dials turn perfectly on it, and also leaves room for some potential long-term relaxation, right? So all of these models said that it formed within 100 million years of the formation of the body, and so the solar system's, 4.4 billion years old, so that's a lot of time for it to just sit there, so it might have actually been shrinking through time. And also this 100-kilometer lithospheric thickness, this mechanical layer, is sort of pretty closely correlated with the spherical harmonic 2 or 3, so that wouldn't also likely change it because the membrane stresses are just starting to become important. So this work was able to reproduce the bulge of Iapetus through folds in. If you have this pole to equator variation in surface temperature, you have a heat flow between 0.5 milliwatt and 1 milliwatt, and you have this epoch of planetary contraction, which is sort of a key detail, but is in all of the models that even the sort of tectonic origin, even the rotational models, they think this rotational epoch happened. So all of this work was done through LPI and NASA and my advisor Andrew Dunbar and this Cassini data analysis program and the Airno Space Plan, and it takes a while to get this stuff done, but it's worth it, and it was a lot of fun to do. And so with that, I'll take any questions that you guys have.
Great questions.
I don't know which one specifically, but I've heard that some geological activities in other moons, I think maybe Europe, are affected by its host planet's massive gravitational effect, where you get this type of effect from its host planet. That was not mentioned at all. This talks of, do you assume that that's by no means a mechanism that could produce this bulge or contribute to it?
Yeah, so yeah, you have this orbital resonance on some bodies, primarily Enceladus and Dione. and then you also, it's more famously known in the Jupiter system, where you have Io, Europa, and Callista, and Ganymede, sorry. Iapetus is fairly far out in terms of orbital distance from Saturn, which is actually likely why this model works for formation, because if you had this orbital resonance, you would have a higher heat flow over the duration of its existence, which probably would have cooked it out, which is why you don't see it in a lot of bodies. So you need a couple of, it needs to be sort of a special case where it's far enough away to undergo this, this sort of porosity loss and not be in an orbital resonance.
With regard to that type of reason, it seems like the binary case that you were describing earlier, where I guess dissipation of energy causes the two bonds to coalesce, it seems like there would be some displacement, consequently some thermal activity in the interior, and then the third body too would be contributing to that way now.
Do you, sorry, do you mean the, oh, okay, so so that likely happened a little bit after the formation of the bulge, and it also probably happened pretty slowly, more like a snowfall than like a landslide, as it sort of slowly rained down on the surface.
And then you mentioned a 16-hour period with an event like that, say a binary system that has something characteristic of that?
It's possible that that could have sped up the rotation, sort of like a gravity assist, but it might, depending on the exact parameters, the smaller body might actually speed up at a cost of stealing some angular momentum from the bigger body, right? Because all that stuff has to be conserved.
Any other questions?
Is there any future missions planned for these systems?
So Titan just got selected as part of what's a discovery class, which is a smaller class mission to fly basically a drone onto Titan and have it visit a series of lakes. It's competing against one other moon, or a small body in the asteroid belt. So I'm hoping that Titan gets selected. We are, but that we won't know that for a while. So that's probably not going to get there till around the 2030s. We're currently in, we're getting close to launching in a couple of years Europa Clipper, which is going to fly to Europa and take a couple years, hopefully, worth of images of Europa. And then there's some talk of maybe a smaller mission going to Enceladus, but there aren't a lot of, these missions are expensive, and there aren't a ton of opportunities to do them.
You mentioned that you were modeling the surface temperature to be between 50 and 100 Kelvin.
Mm-hmm.
What do you think the subsurface temperature is like?
So a lot of that depends on what conductivity value you use. Do you think that ice is convecting? I think it's unlikely to be on Enceladus, on Iapetus. And then, do you think? And what do you think the heat flow is? So I think that basically it's pretty likely the heat flow is low, and that the conductivity is going to be between those two parameters. So I think at about 200 kilometers depth, you would have somewhere on the order of about 250 Kelvin, maybe getting up to 270. I mean, I think these bodies are pretty cold, and there's likely a small liquid ocean, really deep, but just due to the pressure, right? Because as you go down, you need a much it can be much warmer and still be ice, but not forever.
Yeah, 250 Kelvin is still, it's cold for Earth, but it's still Earth.
Right, but sorry, that's just sort of the mechanical lithosphere. I mean, you'll get liquid water, but it would be unpleasant to be in.
Other questions?
In the case where you have, I guess, the equatorial bulge and icy world, I mean, things start to match up here, but could there be another candidate for the icy world that might demonstrate the reasons for the bulge to exist? Or is there another way to test this?
So it doesn't look like there are any other places within Jupiter or Saturn to test it. We only have data from the 70s from Uranus and Neptune, which also have icy worlds. So it's possible that one of those has it. I mean, we see so much diversity within the Saturnian and Jupiterian systems that it's hard to disprove some of these theories just because there's so much variation. So there's also talk about what's known as an ice giant mission to either one of those moons, planets, to do some follow-up work. It would be neat if there was another one, but
for say in terms of the finite element model, for instance, demonstrating why there is an equatorial bulge in this case, but would it, say if you apply it to another body, icy body, would it predict the same thing, or would it demonstrate what? I think we were fairly descriptive.
Well, it would. So the finite element code doesn't really care what body it is, but the other target satellites would either be too small and so not have enough heat, or too close to Jupiter or Saturn and so might be more likely to be in an orbital resonance, which would then cook out the heat more quickly. So it's all about that heat budget.
There's another question about that.
He answered his question.
Okay.
Is this type of research primarily just fact-finding, or are there lessons that learned that can be applied to your environment?
Well, that's always a fair question. It's always about sort of trying to understand how things form and why they form, and what are some of the consequences for the ice sheets and how they flow. I think it's sort of just a general trying to improve our knowledge, which I like, but isn't for everyone.
All right, let's thank our speaker. And, two quick announcements. First off, to the undergraduates in the class, if you haven't picked up your paper or dropped off the one from last week, we have it on right here in the front. Also, next week we're going to have Heath Skinner here, who's going to be coming from radiation oncology at MD Anderson, so it's going to be a little bit different than what we have been doing. And then the week after that is spring break, so there won't be a seminar that week. So that's the week of the 12th, there won't be a seminar, but we'll be back on the 19th. So I'll see you guys then.